Water at 60 degrees Fahrenheit flows through a 2-inch cast iron pipe at a rate of 130 GPM. Determine what F and HF are for 200 feet of this pipe. So as we're looking at this, we're going to be using our Darcy-Weisbach equation to calculate out the head loss due to friction. So HF is FL over D, V squared over 2G. And then we have to determine F. And so we have one of two different ways to determine F. We can use the Moody chart, or if it's laminar flow, we'll be able to go and use the equation that is just 64 over the Reynolds number. Okay, so one of the first things we got to do is we need to know some properties of water. If I look up water at 60 degrees, I will find that the kinematic viscosity is 1.21 times 10 to the negative 5 feet squared per second. I like using water at 60 degrees Fahrenheit just because since I loved Back to the Future as a kid, I can remember what the kinematic viscosity, since it is 1.21. If you have no idea what I'm talking about, go see the movie and you'll figure that out. The next thing that we need is we need to calculate out a Reynolds number. So our Reynolds number based on diameter is going to be VD over mu. I do not know velocity. I do have my flow rate. So Q is 130 gallons per minute. Can't stress this enough. A lot of students will sit there and go, oh, that's velocity. It's not, which is why you got to pay attention to your units because it's going to tell you if you're making a mistake. So to convert that over, I want to get this into feet per second. So what I'm going to do, well, 1 minute is 60 seconds. So that gets me gallons per second. And then I have 0.1337 cubic feet per gallon. And so if I convert all that out, that's going to give me cubic feet per minute. So after bashing that in the calculator, we should get 0.289 feet per second, cubic feet per second. So we'll go plug that into Reynolds number. 0.289 cubic feet per second. Going to multiply that by our diameter, which is a 2-inch cast iron pipe. That's 2/12 of a foot. Dividing that by our kinematic viscosity, 121 times 10 to the negative 5 foot squared per second. Now we take a look at our units. We have foot squared down here. We have cubic feet. Oh, no, see, I did not divide by the area. And this is where the units comes into play, because looking at that, it's like, oh, wait a second, that is not R. That can't be right. So let's erase that for a second. And since we made a mistake, now we know we made a mistake that we caught with units. Q is equal to velocity times area. So velocity is Q divided by area, 0.289 cubic feet per second. Divide that by the area, pi over 4, 2/12 of a foot. I'm just using that to do our conversion more quickly than writing out times, 1 foot is 12 inches. And then once we get that, we've got 13.28 feet per second. Now if I go and plug that in, okay, that's 13.28 feet per second. Ah, there we go. That looks better. We have feet that are going to cancel out. Feet squared on the top, feet squared on the bottom, second, unitless parameter. That's what I want. Reynolds number of 1.83 times 10 to the 5. Turbulent flow. So what do? I'm going to have to use the Moody chart. Since I need the Moody chart, let's take a look at the Moody chart. So what two pieces of information do I need for the Moody chart? Well, I need Reynolds number, which we just figured out, which is 1.83 times 10 to the 5, turbulent flow. I need epsilon over d. So if I go and I look in my book at my table, 0.00015 feet. So epsilon over d, that's in feet. This has got to be a unitless parameter, 0.00015 feet. I'm going to divide that by my diameter. And my diameter, once again, in feet is 2/12 of a foot. That will give me 0.0009. So 0009 is not on this chart, but it's going to be right in there. So we'll figure that out. So now I've got 1.83 times 10 to the 5th. There is 10 to the 5th. That's 1.5, 10 to the 5th. There's 2. So I'm going to say somewhere in there is our 1.83 times 10 to the 5th. And so there's my 0008, 001. So I know that my guy is right in between the two of them there. So that's going to be about right there. And then I'm going to read that over. It's approximately right there. So by the chart, F should be 0, 2, 1. So there's the first part of my answer. So now that I have what my Darcy friction factor is, I can go back to the Darcy-Weisbach equation, calculate out what my head loss is. So the head loss due to friction is FL over D, V squared over 2G, with F being 0.21. The length of my pipe given in the problem was 200 feet. 2/12 of a foot. Once again, got to make sure that everything's broken down to where the units will cancel correctly. V squared, we calculated out V was 13.28. And that's square, let's write the units in. Don't want to forget that. Feet per second. Square that. Divided by twice gravity. Remember English system, 32.2 feet per second squared. Feet will cancel out. Second squared will cancel out. You got feet squared over feet, so that'll give me feet, which I should be getting a head loss in a unit of feet. And so when I calculate that out across 200 feet of pipe, we're going to lose 68.9 feet of head. And that's our head loss due to friction.